In this video, we'll discuss the quantile regression case study on income versus food expenditure example. Let us introduce the case study. You are an economics researcher and want to study income versus food expenditure in certain localities of your hometown. Now you have collected data for 235 individuals on these data points like food expenditure and income, and you believe that there is a considerable heterogeneity in your data. For example, there are people from low income, people from high income and expenditure domains. And therefore, the typical conventional OLS-based mean models may not do justice to your analysis. So you'd like to employ a novel quantile regression tool for the analysis. Now, start by loading the food income data. The data comprises income and food expenditure for a set of families. And then we need to do the following analysis. These are the analysis points. First, you need to visualize the data with mean and median quantile regressions. Then you have to, on the same plot, add quantiles from 5 to 95 percentile and examine the behavior of these regression quantiles. Then run a quantile regression function for median, summarize and interpret the results, conduct statistical inference using hypothesis testing procedures for the quantile regression results, then perform quantile regression for quantiles using 5 to 95 percentile and an interval of 5%. Also conduct the joint test of slope difference for the three models. So you have three models, if 25, 50 and 75 percentile. See if their slopes are statistically different or similar. That means whether there is a heterogeneity in the data or not. And then also separately conduct the in combinations of two. So in the combinations of three, the exact picture may not come out. So we'll also try in the combinations of two. Finally, to conclude the analysis, we'll generate the regression process, the complete regression process, and visualize the same. We'll also compare the goodness of fit using AIC values from the regression and also goodness of fit, which is R square from this particular paper, Coenker Machado, 1999. And then lastly, we'll break the data into test and training data set. We'll train a regression quantile model and compare with a simple OLS model and also visualize the results. In this video, we start the case study analysis on food and income expenditure data. First, we'll set the working directory, go to the session tab, set working directory, choose the location where data and other files are. Once I click on this button, notice a command has appeared here. For future reference, I'll copy this command. If I've set the working directory correctly, on this file tab, my data and other files would be available. For example, I'm going to use this food income data and this is appearing on my file tab and therefore it is ready to use. Now, as the next step, I would like to load the relevant library packages. I have already installed these packages, so I need not do that again. So I'll install the relevant, rather add the relevant packages to. So since they are already installed, I'll straight away add this library command. If you're familiar with R, this command, first I'll add the quantrec package for quantile regression. I'll add tidyverse package. This is also useful for data analysis and ggplot and other things. And lastly, there is WRTD as this package for some quantile regression analysis, some advanced analysis. Now with these commands, I have loaded the relevant packages to my current working directory, so they are available for me for the current use. The next step is to read the data. So for that, there are two approaches. First, I can directly sort of click on this read and click on it here. So this is one way to read it. The other approach which I generally prefer is to write a simple code and read RDS. And here I can write within quotes, my data is in food underscore income dot RDS form. I can run this command as well. Now, if I have read the data correctly, let me show you a couple of. So if I run this with head command, head data, it will show me some initial few elements of my data. You can see that some initial elements, there's income column, there's food and expenditure. There's also something called glimpse command, which I can run to see a brief overview of my data. You can see it has 235 rows, two columns. There are two columns means two variables, income and expenditure. Both of them are numeric. DBS for double or numeric in case of R. So this seems that we have read the data correctly and we are ready to start with our data exploration and quantile regression analysis. Let us start formally with our data exploration exercise. In the first question, we are supposed to visualize the data with mean and median quantiles regression quantiles. Now, to achieve this step, we'll make use of the ggplot, which is a very advanced form of plotting or called as grammar of graphics. So first and foremost, I'll write this layer by layer. I'll write first ggplot command, food income. So this is my data. And in this data, I'll specify my aesthetics, AS for aesthetics. First, the x-axis is my income. You can change the axis also, but I'm putting x as income because this is my independent variable, and dependent variable is food expenditure. So this is my dependent variable. If I run just this command, you notice an empty plot is created. So R knows that ggplot knows some kind of plotting is to be done, but what some other parameters like what kind of scatter plot or what kind of plotting is needed. So first I'll give geometric object. You need to supply the geometric object, and in this case I'm using the point object. If I run it, you'll notice dark points are plotted, but I want some color for the effect, so I'll use the green color maybe. So now you have green plots. Second, I would also like to add some quantiles here. Maybe I would probably add, let me add some geom quantiles here, underscore geom quantile. Now I'll add these quantiles with red because I've already used green, so red would look nice. And I'll specify the quantiles that I want to plot. So I'll add, for effect, I'll add quantiles, median quantile with a slightly higher line width of 2. So this would give some nice plot. So you have the median quantile plotted. Also, I would like to pitch it with the OLS kind of model. So what if along with this median, would median and OLS, which is a representation of means, conditional means, is same or how different it is? So I'll add the smoother, and the smoother method I'll specify as OLS. So OLS specified with linear modeling LM. LM specifies are that linear modeling or linear plot is to be added. If I did not add that, you would find the output very interesting. You'll have a non-linear kind of setup, but I don't want this non-linear thing. I want more of a linear kind of setup. So method equal to linear, and I'll change the color also. So maybe a color of blue color, and line width also, maybe a line width of 2. And you can see there are some bands. These are because of standard errors and interval estimation, which I would like to remove. So this standard error equal to false will remove those bands. And now you can see we have a very nice blue and red line being here. Now the difference is not much, which suggests that while at mean and median, the relationship is not too different. The average relationship with the OLS regression as depicted by the blue line, and the median relationship at 50th percentile with red line is not too difficult in terms of slope. They are very fairly close, which means there is a lockstep one by one, 1-to-1 relationship, 45-degree kind of line relationship between income and food expenditure. But our hypothesis is that while at mean and median they may be same, but across quantiles there may be substantial differences. So we'd also like to visualize this relationship with regression quantiles across different quantiles. So let's see how to do that. So I would like to visualize my data in addition to mean, median, and other regression quantiles. Now for that, you need to first specify what quantiles you want. Now for simplicity, we'll use only 10 quantiles or what you call as deciles, which can be easy generated with this sequence command. So the sequence command will generate the nicely spaced quantiles for me. So let me show you what I've generated. So you can see 0, 0.1 up till 1.0. So I have nice quantiles. Now I'll not write the full code. I'll make use of my existing code because I've written already. Already I've made that effort. So I'll just use, and this is the power of ggplot. I need to only define my quantiles. I need to just slightly modify my quantiles a bit. And the problem here would be the color is red. So all those quantiles would be plotted with the same color. So you can see it doesn't look so good. So there's a very interesting parameter through aesthetics arguments which I can supply. A is alpha. This alpha arguments will ensure that these quantiles are sort of plotted with different transparency. So I can differentiate between them. You'll see the lower and higher quantiles. And when I run this, you'd notice now there is a difference in transparency. For example, the lower quantiles are more transparent while the upper quantiles are more dark. So these upper quantiles represent the relationship at higher quantiles. And now, just before discussing the graph, let me make it more publishable and good aesthetic. So I'll add the labs. So first is the title. I would like to add the title plot, which is food expenditure versus income. Second, I would also, for the effect, for just for the knowledge, I'm adding the x-axis with this income and y-axis with food expenditure. So now this plot should look good and aesthetic. Now just let us discuss the interpretation. Now you can see at the low, if you look at the lower quantiles, these are the relationship is lower. That means for these guys at lower quantile, smaller the food expenditure is small, relatively smaller as compared to income, while for at upper quantiles it is higher. So the guys at the upper quantiles probably they are going to fine dine kind of restaurants and spending a lot of money and so on. Although there is another additional analysis that I am not showing here. If I compute food expenditure as a ratio of income, then it would be a smaller number for these upper quantile guys, which is interesting analysis. But if in terms of absolute numbers, the food expenditure is a rather bigger expenditure for these guys in absolute terms. Let me just quickly show you this kind of analysis. What if I'm not looking at absolute numbers, but rather food expenditure as a sort of fraction of income, and something interesting will be revealed here. I'll just simply modified my y-axis. It is now food income to expenditure. And now you can see when it's not absolute number, but actually the food expenditure as a per unit of dollar or rupee of income, you can see the relationship is declining. That means as you move towards higher income levels, their expenditure with respect to their income per unit of income, it decreases as compared to the lower income groups, which is an interesting analysis because on absolute raw basis, they were spending a lot of money in their food expenditure at higher income levels. But when you move to the higher food expenditure per unit of income, then you'd realize that this decreases as income decreases. For more analysis, we'll move on to our quantile regression shortly. In this video, we'll run a quantile regression for the median and then we'll summarize and interpret the result. We'll also try to conduct the statistical inference using hypothesis testing procedure for these quantile regression results. So as a starting point, let us run quantile regression for the median. That's simple. You have to just specify the model. Then RQ command, this RQ will run the quantile regression. All you need to do is specify the dependent variable, which is food expenditure, and regress it on the income variable. Also, you have to specify the median quantile explicitly here. And X, data, you need to provide the data, which is food income. This is one simple way to run this regression model. I can just use this summary command and you can see the output. So we'll focus less on intercept, we'll focus more on income. You can see there is a very lock stock manner, almost 56% on median, at median level, almost 50 for each 1 rupee or $1 increase in income, the food expenditure increases by 0.56. So almost you can 56% of their money they are whatever they get, 56% is being spent on food. So this seems to be the case. There are other approaches also. You can change the method. For example, you can use other methods. For example, there is something called for the same you have method equal to, you can change the method. For example, here you can apply method equal to fn. This fn is for Frisch Newton fn. This fn is for Frisch Newton algorithm, and you can again possibly there'll be, so coefficient is not changing, so not many changes with fn. Again, probably that existing results were the best. You can also, there's something called pfn, which which is another modified version of Frisch Newton. So if I summarize that, there's a warning which is not a big worry. So results are similar. So not many changes. So we'll stick to the same results. Now you would like to do the hypothesis testing, whether these results are statistically significant or not. And for that, you need to specify what kind of standard errors are required. So for hypothesis testing, you need standard errors to calculate the t values and so on. So now while running the summary command, we'll modify them a little bit. Specify our standard error procedure. For example, standard error can be NID standard errors. You can read more about their description. You can type the question mark RQ and you'll get all those parameters. For example, if you what kind of method you want, so BR method is there and FN and so on and so forth. You can see some of these in the summary, and you can also If you want to know what kind of standard errors are available, you can just type this summary.rq and just see if you have rank, IID, NID, and their description KER and so on. So for example, I can let me first run this one. So if I run this, I can see the t values are pretty significant. So that means the status, this hypothesis testing would tell us that this is indeed non-zero and very significant. Similarly, there are others, for example, KER kernel. So here I get again very significant result and so on. So you can apply more. For example, there's bootstrap standard errors and so on. So you can you're getting very similar results. So here overall we can conclude that with this statistical inferencing and quantile regression modeling corresponding to the median, that there's the coefficient is 0.56. That means almost 56% of their income is spent as food expenditure, but that is at median level. In the next video, we'll run it for other quantiles also. Now that we have run our quantile regression for median quantile, in this video, we'll run the quantile regression for other quantiles also from 5% to 95%. And we'll also do their statistical inferencing with the hypothesis testing bit. So for that, first we need to specify our quantiles. So let us start with this very simple command where we specify quantile starting from 5 to 95 with an interval of 5 and we'll divide it by 100. So this will create the relevant quantiles for us. Now with these quantiles, we can start our quantile regression analysis. As a first step, we would like to use this model command with RQ. RQ is the simple for quantile regression. Now our model will remain very similar that we saw earlier, food expenditure regressed on income. The change here is that now revised quantile will be, instead of 0.5, I'm writing here tau, and tau we have already seen it starts from 0.05, which means 5 percentile to 95 percentile. We need to specify the data. So data is food income. Now if I run this, first, I'll run the raw results without any hypothesis testing, and you'll see for each quantiles there's some warning. Maybe some places output may not have converged, but still, just see. So you have these results corresponding to lower quantile. At lower quantile, the result is 0.34. That means for at lower quantiles of food expenditure, you have 34%, and as you increase the at higher quantiles it increases, the range increases almost 70% of the money, this thing. So you can see at certain quantiles even 70% of the food expenditure is going as a part of income. 1 rupee increase, out of this 70% is going into food expenditure. Now if you want to attach the hypothesis testing, so the relationship is not homogeneous, it's heterogeneous. Now you can, if I run it, you can also see the hypothesis testing, and my coefficients are also very statistically significant. That also we can see. So all these coefficients are statistically significant, and we can see as food, there is a considerable heterogeneity. There's a lower quantiles of food expenditure where a lower amount in expended as a food, and higher quantiles of expenditure where a higher percentage is spent in food expenditure. So with quantile regression, we realize that our mean result, which describe the median or median quantiles or mean average results, are not consistent for other quantiles of income. For example, at lower quantiles of food expenditure, we have relationship where lower coefficient is obtained, and there is also higher quantiles of food expenditure, the relationship is higher. That means a higher percentage of food expenditure as a part of income. So although this is a slightly surprising result, but just to put things in perspective, this result suggests that at higher people who are spending a higher amount of food expenditure, there for a given change in income, the spending on food is higher, almost 65%, as we can see here, 65 to 68. While those who are spending lower amount on food, their expenditure is lower, or maybe around 30 to 40% range, which is a rather surprising result. In the previous video, we saw that across different quantiles of food expenditure, there was considerable heterogeneity in the relationship between food expenditure and income. But we would also like to see whether this heterogeneity is indeed statistically significant or not. So as a starting point, we would like to test, and we'll test for different relationship for three quantiles, tau equal to 25 percentile, 50 and 75, which can be done through sort of hypothesis or joint test of slope differences. So we'll test for joint test of slope differences. First, let us compare for 25 percentile, 50 percentile, and 75 percentile. So this can be very easily achieved with a very simple ANOVA command. For example, let me show it. So I have a model RQ. Now here we are running this food expenditure being regressed on income. And now I'll specify tau as three quantiles only because our we want to understand this thing. So we'll just use for the time being three quantiles. One is 0.25, one is the median, and another is the third 75 percentile. I'll specify my data. Data is food income. So now this will have the output of three models. So for example, if I summarize this for you, you'll get three models. Now the question we are asking here, there are three numbers we have. For income, we have 0.47. For 25 percentile. For median quantile, it's 0.56, which you already saw in the first go. And for 75 percentile, it is 0.64. Whether these numbers are statistically significant and different or not, first, so if you want to know individually they are statistically significant, we already saw they are, but still, let me show you some kind of standard error measure, and you can see they are. So individually they are, but is there a significant difference between them? That is not clear from this. So individually they can be different from zero, but between them, are they different from zero? So this ANOVA test, if I run this ANOVA test on this model, this ANOVA test checks whether these three are same or not. So kind of null here is that all three slopes are same. All the three slopes are same. Now, this hypothesis is rejected. The only problem here is that we are fitting it jointly. So while at least one of them is different from two, from there we can infer that at least one of them, one of the slopes is different from the other two. But we can't say how is the relationship between, let's say, 25 percentile and 50 and 50 and 75. For that, we'll individually conduct test individually for each of the two quantiles. So for that, we'll individually fit the test. First we'll compare, and I'll just borrow the same command. So first I'll conduct it for 25 percentile and median. And if I run that, and then I'll simply conduct a typical ANOVA. So I run it for fit one, which is there. So we can see one and two are different, significantly different. Similarly, I'll conduct the fit two to test between 0.25 and 0.75, and I'll run it. And you can see here, they are also very significantly different. Fit two is also different, and fit three, I can test fit three also. Now I'll test between median quantile and third quantile, and they are also significantly different. So we can see here that all three of them are significantly different from each other, and we already know their ordering as well. So the ordering was visible here. So for example, this is the lowest, then there is again significant increase as we just checked, and then so all the three are significantly different and their ordering is also visible now. So this is a very useful analysis. So till now in the analysis, we have been focusing on specific regression quantiles, but we would like to see how many maximum quantile analysis it can generate, how many maximum quantile regions we can generate the quantile regression analysis. This is called quantile regression process. So in this video, we'll examine the quantile regression process, we'll visualize it, and we'll also see some goodness of it measures with AIC values and R square in the context of quantile regression. The typical R square doesn't work, so we use a modified version of R square, which is provided by Coenker Machado 1999 paper. So first we start with the quantile regression process and visualize it. The procedure is pretty straightforward. I'll borrow the previous command. For example, let's call it model underscore process. Now, in this process, you have to provide the same regression quantile command. So everything else remains the same. Food expenditure being regressed on income. But for tau, the only change is that you have to provide this -1 negative value, which is not feasible. When you provide such value like -1, which is not feasible, it generates all the possible quantiles. And so we'll run it. Now, this produces a very cumbersome kind of output. For example, if I print this model underscore process, you'll see a very lengthy output, which is difficult to sort of manage. So there are so many data points here, which will be, for example, if I want to see this only the solution part of it, this model process, it would be very tedious to interpret the solve. And you can see the tau, q bar, and various values. There's also another, there are various sort of information point. If you want to see that, you can apply the structure command to this model process, and you'll see it's a very heavy output. So it's difficult to sort of very unwieldy and difficult to contain. So the easier way to do this is to use this plot command. So if I run this plot command of model process, this will be very useful. It gives me both the coefficient and intercept across the quantiles, and we can see how the maximum quantiles are being generated here. I can zoom it out so you can see here. It's a very interesting plot. It shows that starting from lower to upper quantiles, how the relationship increases. We, for the time being, we are ignoring the intercept. We are more focusing on the coefficient of income, and you can see there's a consistent increase starting from 0. Approximately 35 to 0.7. There has been a gradual increase. Next, we would also like to add AIC values and compare the fit of the model. So first, let us start with addition of AIC values. For that, to extract the AIC values, we'll simply use this model command. Now, let's suppose I want for all the quantities RQ, and you have food expenditure, again regressed on income. Tau, we can again use the same tau that we have already calculated, and data equal to food income. Now, the next thing you, so this is there. Next, I'll use this, I'll create a new sort of data frame where I will have my, in the form of table, where I have model is equal to, now paste, this paste command would be very useful here. So tau, and I'll use tau here. So the quantile will be pasted, quantile values will be pasted, and AIC, I'll use the AIC of the model. The model that I have already run here. Now I need to provide AIC of the model. So I'll run, let's call it model, and if I run it, let me print it. If I print it, see for every quantile, different model, the AIC values are provided. So you can compare, the lower the AIC, the better. So you can see the lower value, wherever you find the lower value, that gives you the idea of higher fitness across different quantiles where good fit is obtained. There's also, so you can see 2952 is pretty high. The lower ones are at 2820. So this probably 2821 is and 2820. These are the lowest values, around 60-70 percentiles. So these seems to be the lowest values. Now, in addition to that, you'd also like to know the goodness of fit measure, which is provided by Quenker and Machado. So you'd like to add goodness of fit measure. For this, you have to first specify a naive model against which you are computing the goodness of fit. This is a typical residual R square approach where you have a naive model. So first you have a naive model where we are saying that we simply use one constant value, and the mean model equal to 0.5. This is our typical, and data equal to food income. So this is our typical naive model. In this naive model, we specify another model 1. Let's say this is for only one quantile we are doing, so 1. And now I'm specifying income. So you can specify the income. Now this good fit command, you can apply this good fit command, and first you provide the residuals from model 1, compare them from the model 0, and you need to specify the quantile which we used, which is 0.5. So you get the 62%. So this is 62% kind of value. Now if you want to change the quantile, nothing doing, you simply, for example, rather than doing this, I'll put 0.25. So if I run it for 0.25, you can again find your good fit value. It has slightly decreased. And similarly, you can compute it for 0.75 also to compute the good fit value. Its interpretation is similar to that conventional R square. That means your model is able to incrementally explain 70, almost 70% in this case, as compared to your naive model. So the model fitness is almost 70%. You are able to explain as compared to the naive model where there was no variable. In this video, we'll conclude our quantile regression exercise. First, we'll break the data into test and training data sets. Then we'll train a quantile regression model and a linear regression model. We'll compare both the models and visualize the results. So we will train and test our model quantile regression and OLS regression and compare the results. So first and foremost, let us specify the quantile. So we'll use deciles now. So first we have tau. It's a very simple way to obtain the quantiles. So if I print it, we get quantiles from 0.1 to 0.9. Next, we'd like to break our data into training and test data set. So as a good practice, a breakup of 30-70 test train or 20-20 test train is good. So we'll start with the train data set. So in the training data set, I'll have food income, and we'll use initial 150 observations to train our data. So this will be our training data set. So let me show you train. And similarly, we'll have our test data set, which will have the remaining observations. So we'll use the remaining observations from 151 to 235. We have overall 234 observations for training the data set. Now, first let me train our quantile regression model. Let's call it model underscore RQ. This is regression quantiles food expenditure regressed on income for all the quantiles, and data used is training data set. Similarly, I'll use my OLS model, model underscore OLS, and in this OLS model, LM food expenditure income, and I'll again the same data set, train data set. So I have trained both the models, the quantile regression model and OLS model. Now I'll do the prediction exercise. That is simple. So first I'll predict from regression quantile model. Let's call it pred RQ. This pred RQ object will contain the predicted values for all the quantiles from, but now prediction using test data. So for example, here, sorry, I need to do predict. Now, if you want to know what is inside this spread RQ object, you can just do this. And you can see for all the quantiles, I have my predictions from 151 to 235 for all the quantiles. Similarly, I'll use my OLS object and store my, let's call it pred LM, because that is linear modeling. So again, predict, but now I'll use my OLS object with test dataset. So if you want to know what is inside this spread underscore LM, you can see it will have only the corresponding to mean results. Now we want to sort of visualize them, and one way would be, so first and foremost, let us plot our, so I'll create a base plot where I'll plot the typical OLS model. So I'll plot first food underscore income, and here I'll plot my from 151 to 235. These are your actual predicted values of income, and we'll plot them along with the predicted objects. So the actual values along with predicted objects. The type is line. We'll give it color as blue and line width of 2. So it may be a good line. So this is our typical OLS line, predicted line with OLS. With the actual values, these are the actual values on x-axis. On y-axis we have predicted values. Now we'll use a small trick. What we'll do is we'll run the loop 9 times. So we have 9 observations from 0.1 to 9 quantile. So I will run from 1 to 9. I in 1 to 9. Our loop will run 9 times. And we'll add up the quantile lines. So lines, food, income, and the same object in the line. The x-axis remains the same. So we are not changing the x-axis. The x-axis remains the same, but now we'll change our prediction object, which is spread underscore RQ, for each I separately. And color, probably it would be easy to make the color dynamic with each changing I. R understands each color code as a number also. So for each number, there's a color assigned. So I'm using that property for my benefit. And line type also I'm changing with I. So line type also I'm making dynamic with each I, and color also. So if I run this code, you'll see all the quantile lines have been plotted. So I have different lines for each quantile. So now I have a good comparison of predicted objects. So you can see how predicted objects differ across different quantiles. The the mean line, the blue one, predicted objects from OLS, and then for different quantiles, the predicted objects. So you can see how the predicted objects differ for different quantiles, and they are plotted vis-a-vis actual values. Now, of course, you would understand the difference that when you are using actual values, the actual values may come from different quantiles of income. For example, those who have low income and low expenditure, those quantiles also, and high quantiles. So it's a mixed bag. So when I compare them with the predicted objects, you can appreciate that there will be differences. So for example, those lines from lower quantile, they would fit better in the lower segment, while those in the upper quantile, they would fit in the upper quantile of data, and therefore the overall picture cannot be consolidated with one simple average mean line.